Hello, this is Susan Poss, and we are still working on graphing linear equations. I'm in Chapter 4. This is Section 3, and this is my first video. So I've numbered it 4.3.1. So we want to start off here with the definition of slope. Slope has to do with how steep a line is, how flat it is, what the slant of the line is, and some of the applications of this, of course, are the steepness of a roof line or the steepness of a financial model curve. So these are all things that have definite applications in the real world. Slope is defined to be the rise over the run. If the top number is positive, you will count up. If the top number is negative, you will count down. If the bottom number is positive, you will count to the right. If the bottom number is negative, you will count to the left. So the top number has to do with up, down, rise, and the bottom number has to do with horizontal run, left, right. Another definition for slope is the vertical change over the horizontal change. Sometimes in mathematics you'll see that noted with a delta symbol, delta y over delta x, which is the beginning step in learning calculus when you start to talk about a first derivative and a rate of change. So the definition of slope, it uses the lowercase letter m. I think that comes possibly from René Descartes' French background, meaning monter, to climb. I'm not sure about that, but m is the letter that we use for slope. Excuse me, and it's the change in y. So you see y sub 2 minus y sub 1 in the numerator, and the change in x on the bottom, x sub 2 minus x sub 1. Those subscripts don't have anything to do with arithmetic, like squaring or cubing or anything like that. They just identify first and second. So when you see a sub 2, that's different from a sub 1, identifying a first value from a second value. All right, so, and here's a little important little piece of information. X sub 2 and y sub 2 cannot be equal to each other, because if they are, then you would have a 0 in that denominator. So that's the thing that we'll be interested in when we start talking about undefined slope. Right, so here are some examples. We've been given a series of a pair of points. The first one you see has coordinates 3, 1, and the second one has coordinates 2, 6, and I have gone ahead and labeled those. The first ordered pair, you see I'm using subscripts 1, so x sub 1, y sub 1. The second ordered pair, I'm using subscripts 2, x sub 2, y sub 2. And then I've written down the formula, and now I'm ready to substitute the numbers in. So y sub 2 is 6 in this problem. Y sub 1 is 1. X sub 2 is 2. X sub 1 is 3. The order is critical. If you get the wrong order, you're going to get the wrong slope. So in the numerator, I have 6 minus 1 is 5. In the denominator, I have 2 minus 3 is negative 1. And you would probably just want to go ahead and write that as negative 5. Although generally for slope, you do want to have two numbers, so that one is a rise and one is a run. And you can see as you look at these two right here, these two expressions are the same. They are equal. They are written differently, but they identify the same slope. All right, so moving on to the second example, here are our 2 points. You can see I have again labeled them first point, x sub 1, y sub 1, and second point, x sub 2, y sub 2. The order in which you name those really doesn't matter, just so long as you are consistent with pairing the sub 2's on the x's and the y's and the sub 1's on the x's and the y's. All right, so in this example, y sub 2 is 2. Subtract y sub 1 is negative 6. X sub 2 is 6. Subtract x sub 1 is 6. And uh-oh, I have a problem. This is 2 plus 6 over 0. And so this slope would be undefined. And that does happen, and you'll see what that means as we move on through this section. Here's another one where I have already labeled the subscripts, the pairings. So I'm starting with y sub 2 is 2, subtract y sub 1, which is negative 3. Coming back to x sub 2, subtract x sub 1. Let me come on down here. This gives me 2 plus positive 3 on top. Gives me a negative 2 on the bottom. So it looks like 5 over negative 2. You may write that with the negative out in front. Or, let me squeeze it out here, you may write that with the negative in the numerator. So let me highlight these. Negative 5 over 2 is equal to positive 5 over negative 2, which is equal to the negative out in front of the fraction 5 over 2. Here's our next example. We start with the value 13, and we subtract 13, so y sub 2 minus y sub 1. We start with negative 4, and we subtract 0. Made that line a little too long there. And this time you see that I ended up with a with a 0 in the numerator, and that is equal to 0. So if you've forgotten some of this, be sure that you pay attention that when the 0 is in the denominator, we get an undefined expression. If the 0 is in the numerator, that is in fact equal to 0. All right, I think that's enough of those to do right now. Let's look at some where we find the slope not from points, but from looking at a graph, and we actually end up doing the same thing. So I'm just going to do maybe a couple of these. This first line, I see a point that has coordinates 3, 3, and here's another point down here that has coordinates 1, negative 2. And I think you can see that I'm going to do exactly what I did before, which is why I don't need to work very many of these. I'll start with the 3 and subtract the negative 2. Remember, the y's go on top. And then I'll come back and start with the 3 and subtract the 1. So I'm starting with y, subtract y, and then I'm going to x, subtract x, keeping that in the same order. So in the numerator, it looks like I have 5. Oh, excuse me, I made a mistake right here. It should be 3 subtract 1. Sorry. In the numerator, I have a 5, and in the denominator, I have a 2. So this particular line has a steepness or a slope of 5 over 2. And remember, we defined that as rise over run. Let me change to a red color here. What happens is if I start at this lower point and rise 1, 2, 3, 4, 5, turn 90 degrees and run positive 2, you can see the rise over the run signified there. All right, so let's see. Here's a point negative 2, negative 1. And here's a point 1, negative 1. And if I calculate the slope, I would start with a y value, subtract a y value, over an x value, subtract an x value, and again maintaining the order that you started with. So in the numerator, this is negative 1 plus 1, and this is positive 1 plus 2, which is 0 over 3, and remember we said when the 0 is in the numerator, that is equal to 0. So this particular line has a slope of 0. I think that probably makes sense since it's not rising or falling, it's flat. Notice that this one was a positive slope. That one was a 0 slope, and let's quickly take a look at this one. This is negative 3, 3, the coordinates of that point, and this looks like 1 comma negative 4. And calculating the slope, I'm going to start by subtracting one y coordinate from the other y coordinate, maintain that same order. So we talked about that can be written 7 over negative 4, that can be written negative 7 over positive 4, or that can be written with the negative out in front of the fraction. And again, just to show you quickly, if I start at this upper point, if I drop down 1, 2, 3, 4, 5, 6, 7, turn the corner and go 1, 2, 3, 4 to the right. Actually, I guess I'm using this one right here, huh? Negative 7, 7 down, and positive 4. And let me change color. So this is kind of important. I thought this was pretty interesting the first time I learned it. Let's look at this one. What if I start at the lower point and go up 1, 2, 3, 4, 5, 6, 7. So that's a positive 7. And then turn to the left and go back 4. And so you can see that negative 7 over positive 4 and positive 7 over negative 4 will give me the same slant or slope. Trying to see how far I wanted to go with this. Okay, I'll finish this up. Seems like I'm doing a lot here. Slope-intercept form, that is y equals mx plus b for a linear equation. When you put something into slope-intercept form, and you're going to be asked to do that a lot, what you're doing is getting y by itself. So you're going to take whatever equation you have and try to isolate the variable y. Once you have done that, then you can glean some really important information off of the equation. The slope of the line will be this coefficient on the variable x. The y-intercept will be at the point where that constant is. So 0, 3 is the y-intercept in this example. In the next example, the slope is this negative 3/5, and the y-intercept is going to be at 0, 1. So it's important to be able to put linear equations into slope-intercept. So here are a couple that I've already worked out for you. This one's already got y by itself. You see it says y equals 5x minus 2, so it's already got the y isolated, which is what you want to do to get it into this y equals mx plus b form. And once you've done that, you can tell me that the slope of the line is 5 and that it touches the y-axis at 0, negative 2. So you can see we've plotted here, we've plotted you do this y-intercept first at 0, negative 2. That gives you your starting point. And then you use this 5 over 1 to count up 1, 2, 3, 4, 5 from that starting point. Turn the corner and go 1 to the right. And you could repeat that again. Here's 5 up and 1 to the right. And the last example for this video, this equation is also already in slope-intercept form. You can tell me that the slope is negative 2. You can tell me that the y-intercept is at 0, 6. And since this slope is negative, the top number means I'm going to, well, first, let me plot the point first. I'm going to start with the y-coordinate, 0, 6, the y-intercept. And then from there, I'm going to come down 2 and right 1, down 2, right 1, down 2, right 1. And that you can do that as many times as you'd like, and that's the way a negative slope will look. So I hope that helps us get started here in section 3 of chapter 4.